I think the new look of techno this season it's obviously completely different from last season. One of the reasons why it's completely different from last season is, well, the first couple shows of techno last season I shot myself.
Moving into season 2 of techno, we felt one of the most important things that we needed to do was give the look a facelift. So what we did is we said, you know what this show really needs is that white, that stark white, really clean environment that looks more scientific. So we looked at take 5 and we said, well, we can take the white background from take 5 and let's use that white as the look for techno, and it fit that show perfectly.
We've had a producer and a shooter on the set, obviously the whole time this season, so the lighting is perfect, as opposed to kind of being thrown together by someone who doesn't really know what he's doing.
As far as lighting goes, we have 4 lights, actually 5 lights on the set. We have our 2 1Ks, which are used as our key and fill. We have a large key light here, and we fill with an airy 1K, and just enough to put a little bit of light on his face. The 2 back lights here are used to light the background, which is all white, and we can key that element and add any effects that we need to as the background. Another very important thing is a hair light that adds separation. And one important tool on any set is a long pole. When you're working on white paper, you can't always walk on it, but you can always use a pole to adjust your barn doors. Quick tip for techno.
We also increased Eric's wardrobe a little bit. We made him just a little bit more formal.
Clean enough for television.
Kind of like the college professor of the 3 of us as far as his look goes. And it suits the content really well to have him have that kind of a professional look about him.
Dressing with a suit coat felt very natural, very, very comfortable, and it really worked with the black suit coat against the white background.
Then we wanted to increase, along with the white set, not just shoot them on white in the same exact way, but the overall production value of that show needed a boost. So Charlie had joined the team and as a video editor, and we immediately put him on techno, and right away he tripled the quality, the level of that show. It didn't just go up a notch; it went up 3 notches.
So it took me about 4 or 5 episodes before really I was able to kind of branch out a little bit and kind of find a good balance between stuff that they had established and stuff that I thought would probably work inside of techno. I think Eric kind of lends himself to some of the quirky animations and stuff like that. Kind of Bill Nye the Science Guy, kind of funny stuff that at least I find funny. I don't know if everybody else finds funny, but I like putting it in there. So
the focus of very nearly every single episode is the Brent Milby animation. That's the peak. That's what brings the whole episode together, and light bulbs go on in people's heads, and it's just amazing.
Me and Eric will go in a room together and beat each other up for about half an hour, and then we'll talk about politics for 5 minutes at least, and then we'll take his sketches and his diagrams and whatever he's downloaded off the web and come up with the best way to explain it visually.
So across the board, with the new set and Eric's new wardrobe and a new editor with Charlie on that show and Brent's contribution, along with Josh Lieberman as the producer of that show, I can't give enough credit to Josh because honestly, managing Eric and getting him to get things done, not that he doesn't get things done, but managing Eric is the biggest part of producing that show.
Eric and I started working together last year.
Chilled to your liking. Thank you.
Eric began techno as a test, and really as a technical person, it's a different mindset than somebody who's on camera. There's been a transition from techno geek to studio professional, and Eric has really stepped up to the plate. He has a great look, he has great information, and now more than ever, techno has become one of the most popular shows.
With season 2, I was thrilled to see a growing audience, and there were weeks when techno was the top rated episode that week. And I'm really pleased to see that. I think that says that we've done some things right in the changes we've made to that show, and that it's a value, and people are starting to see that, and that's very satisfying to me.
Prompter's loaded, Talon is mic'd. We are ready to shoot techno.
The initial idea this season of shooting on white, I thought that was kind of fun, especially with the idea that I would dress a little more formally this time.
Eric is about 6'9", and which is freakishly huge for an average person. So we have to shoot him on just white. So there's no perspective. You can't tell exactly how tall he is because there's nothing else in the room with him, you know, showing that relationship.
Now, because Eric is shorter than most people, we need to adjust the microphone. We had it a little bit higher before, so this is the proper adjustment.
So do you wear eyeliner too, Eric?
No eyeliner, but this is a good thing for men to learn. A little CoverGirl does wonders. Your skin will look fabulous with a little CoverGirl. This is the Press and Go from Black & Decker. It has a nominal operating temperature of 350 degrees Fahrenheit. This is 228.5 degrees centigrade. Just completely made that up. I have no idea. The secret to ironing here, though, since I'm wearing a suit coat, is that you really only have to iron this area here, and you don't need to iron the back at all. It's a little tip for people out there.
Welcome to the set. Let's do it one more time. We use two microphones on the set of techno. We use both the lavalier and the shotgun. Always use two microphones just in case there's a problem with one of them.
Which never happens.
We don't have problems on techno.
No,
We fix problems.
No problems on techno, ever.
Proper mic placement varies for every subject and every situation. This particular situation, we're going to run the mic through his shirt, and we're going to mount it, and then we're going to hide it just underneath the button. In any production, you always have multiple things happening at once. Over here we have the audio buzz set, and I'm going to steal a piece from the audio buzz set right now. This is an acoustic baffle. This will help control the sound since we're in a very large, very live room.
Now, wait. Did we do these last season? What these were?
We did discuss that, yes.
Okay, and reinforce that I invented these. Yes. This is a flag and baffle. It's a baffle for sound, and it's also a flag to keep out unwanted light. So it's a flag and baffle in German. Now I didn't design this. I just invented the concept, and Billy designed it and built these, of course. But it's a flag and baffle, patented technology. All right, it's not patented.
As you can see here, we have Eric rehearsing his script. This will take about 3 hours.
Features like, oh, your lunch is ready? Thank you very much. Thank you. Our house wine. Thank you very much.
Overseeing techno is kind of like herding cats. They're all over the place. He's funny, he's smart, he's a bit of a curmudgeon. I think Eric on the inside is a very old man, even though on the outside he's kind of a young hipster. Eric is the kind of guy he's going to be a good grouchy old man someday.
I don't know if I believe that. Each week, we squeeze a ton of content into these little segments, and we try to focus on a detail or two that's really important and relevant. Along the way, we often discover some fascinating tidbits that just don't fit into the tightly edited flow of the regular program. And so this week, we present Techno Trivia. I guarantee you'll learn something surprising, something interesting, and almost certainly something that you didn't know before on this segment of Techno. The most common colors for 4-color printing are cyan, magenta, yellow, and black. CMYK. The K in CMYK really stands for key or key plate. In traditional printing, all of the shape outlines, interior lines, and hashed shading are etched into the key plate, which, when inked with black ink, produces a black and white image that has most of the detail. Color is then superimposed with additional color plates. Pierre Boulard's brilliant botanical illustrations from the 18th century are an excellent example of this process. He etched all of the detail onto the key plate and then printed a base image. After that, he etched 3 colored plates for green, red, and yellow. What's even more amazing is that each of the 600 plates in his book, The Herbs of France, was printed by hand. The word broadcast has ancient agrarian roots and is the process of throwing or casting handfuls of seeds over a broad area. Broadcasting. Charles Herald, a pioneer of early radio, one of the first regular broadcasters in this country, coined the term in the early part of the 20th century. His father, William Herald, owned a flour mill and grain elevator in Illinois and invented a number of mechanical farming implements, including, not coincidentally, a seed spreader. The XLR connection was invented at a company called Canon, which is now a part of ITT and should not be confused with the Canon camera company. The XLR connection is also known as a Canon connection or Canon plug. The XLR's evolution starts with the Canon X series plug, which later had a latch added to it in subsequent versions, the Canon XL series plug. Then a rubber coating was added to the contacts and the Canon XLR connection was born. While most of us think of this connection as a 3-pin balanced audio connector, there are actually many different pin configurations and uses for this robust, lockable XLR connector. You'll recall from our discussion of image sensors in EP209 that the pixels on a camera's CCD only record the intensity of the light hitting them, and not the color. Color is generated by subsequent image processing based on a trick where the light hitting any individual pixel is limited to a particular color by an RGB color filter. This is done with either a color filter array over a single CCD or by using a prism and 3 CCDs in a 3-chip professional video camera. The compromise of using a single CCD with a CFA on it is that it does not record the image at full resolution in color. But if 3 chips are good, wouldn't 4 be even better? Going beyond 3 chips in a video camera probably doesn't make much sense. But for digital still cameras, the extra cost of adding another color to a color filter array is not that great. Indeed, there are 4 color CFAs, including CYGM, cyan, yellow, green, and magenta, and RGBE, red, green, blue, and emerald. we throw around a lot of acronyms on techno, like when we talk about CFAs on a CCD or the CMYK color space or the XLR connector. Actually, all of these items are more correctly referred to as initialisms. Acronyms are initialisms that can be pronounced, like NASA or radar. A backronym is a slang word that explains an existing word that has been retroactively changed into an acronym. For example, the familiar International Distress Signal in Morse code is SOS and was chosen by the International Wireless Telegraph Convention of 1889 simply because it's very distinct and easily recognizable. It did not originally stand for Save Our Ship. That's a backronym. Another backronym is DVD, which was originally an initialism for digital video disc. When this optical disc format began being used as a data storage format, it wasn't strictly a video disc anymore. So DVD manufacturers retroactively changed the meaning of DVD to digital versatile disc, and it's now a backronym. Actually, there isn't anything really official about either of those explanations. Incidentally, the word backronym is a portmanteau combining back and acronym. Camcorder is a portmanteau of camera and recorder. And that's techno trivia and English usage for this week. Thanks for watching, and we'll see you next time. It's no exaggeration to say that 50% of the experience of watching a movie in the theater is the immersive surround sound environment. Now that the word theater doesn't exclusively mean salty popcorn, sticky floors, and $10, but also includes a refrigerator, a pause button, and a bathroom break if necessary, surround sound is a very real option for anyone who's authoring DVDs. In this segment, we're going to explore surround sound and how you can take advantage of it in your productions. As with many of the topics we discuss here, I think that you'll find that the technology is pretty easy to understand and use. The hard part is the artistry of the mix. This is techno. The history of surround sound in the home entertainment system would certainly start with monophonic recordings on wires, wax cylinders, and discs in the latter part of the 19th century. Almost 60 years elapsed before stereo recordings became commercially available in the late 1950s. Then, sometime in the early 1970s, quadraphonic systems of various sorts became available. Of course, the center of the modern home theater is the ubiquitous and inexpensive DVD player. Since DVD video players have something like 85 to 90% market penetration, this makes DVD the obvious medium of distribution for most video producers. In a typical home theater situation, we have our DVD player hooked up to a 5.1 amplifier. The connection will be either through 6 discrete analog wires or a single digital connection. In a 5.1 surround sound system, we've got 6 speakers or channels. A left front, a right front, a left rear, a right rear, a center channel, and a subwoofer. 1, 2, 3, 4, 5, and 6, or 5.1. Movies and music mixes are a little different from each other, but by convention, the center channel is for on-screen dialogue and vocals, with some of the mix spilling over into the front stereo pair. The rear speakers are most properly positioned at ear height and to the sides and not at the back of the room. The subwoofer is for low frequency effects, or LFE, and since audio in that range is very non-directional, it can be located just about anywhere in the room. So to listen to 5.1 surround sound content, we need a playback system to decode the signal and proper speakers set up. here's what you need to get started mixing and producing 5.1 surround sound DVDs. First, you need a computer with a 5.1 sound card. Fortunately, most computers come with this by default nowadays. Second, this computer needs to be connected to a 5.1 sound system. If you were mixing in Hollywood, you'd be mixing in a studio on reference monitors. But in smaller studios, this could be a home theater or high-end computer speaker system. The third thing you will need is editing software that has some type of 5.1 surround sound panner. Creating a 5.1 surround mix is technically very easy. This, for example, is the one that comes with Sony's Vegas video editing software, which was the first widely available software on the market with the surround mixer. Let's say this track on my timeline here is my dialogue track. With the surround panner, I would plant my dialogue track squarely in the center channel and in the front stereo pair to give the voice a little bit of positional space. If we had two actors on the screen chatting amicably, they could easily share the same surround mix positioning. If they were on opposite sides of a very large room, you might want a discrete audio track for each, panned slightly to the left and to the right. The music bed would mostly go to the stereo pair and a little bit to the rear perhaps. But what else could we put into the rear channels? This brings us to our first serious problem, and it isn't a technical one. Yes, 5.1 is really cool and easy, but what exactly would you use it for in your productions? For most of us, helicopter flybys and bullet ricochets are not a big part of our everyday work. 5.1 mixing is not the same as 5.1 encoding. So while 5.1 mixing is widely available in video editing applications, software vendors don't always tell you that you need to pay extra for an AC3 5.1 encoder as well. The words to watch out for are 5.1 surround sound support for applications that can mix but not encode. Fortunately, a 5.1 encoder is not as expensive as it used to be, but it still isn't free. If you're shopping for surround sound software, make sure the AC3 5.1 encoder is included, and not just the stereo version of that encoder. The encoding can happen either when you output your finished movie from your video software, or it can happen in your DVD authoring package. In the latter case, you would output a 6-channel mix from your editing software for encoding in the authoring app. As with so many of the topics we cover here on Techno, it turns out that the technology is the easy part. The real catch is that 5.1 surround mixing isn't just 3 times as hard as stereo mixing. It's easily a magnitude more difficult. You also need to keep in mind that your mix still needs to sound good when down mixed in stereo and maybe even mono as well. With the widely available standard audio hardware and speakers, software mixers and surround encoders, configuring your video editing system for surround sound is not really all that hard. And it should be noted, it's extremely fun. If you have any questions about this topic or any others, drop the tech team an email or give us a call. We'd be happy to help you out with this or any other technical questions that you might have. Thanks for watching, and we'll see you next time on Techno. What you see is what you get, WYSIWYG, is a myth. The digital graphics, animations, and composites that you see on your screen are never what your viewers get. Whether you're producing video that will be viewed on a television set, or laying out pages to be printed, getting accurate colors is very difficult, especially when you don't always have complete control over the method of distribution. In this segment, we're going to look at digital media and color space as we try to get color right in the printed world once and for all. This is Techno. how baffling modern technology can seem, multimedia design used to be much more difficult than it is today. Broadcast engineers and print designers really had to have a lot of expertise to get any results at all. Modern editing software now takes care of a lot of this automatically, which is great, but unfortunately it also means that creative professionals are sometimes unequipped to recognize and solve issues that come up. Color in the real world is measured in very straightforward terms of the wavelength of light. 700 nanometer wavelength light is very red in color, while 400 nanometers is violet. Accurately reproducing colors on the printed page is a completely different and somewhat complex story, however. And moving from a computer monitor to the printed page involves complexities like calibrating the monitor properly and getting the temperature of the ink just right. As we all learned in grade school, light can be broken up into separate colors, and all of the colors of the rainbow can be created from a few primary colors on our paint palette. If we take our primary colors from grade school, red, yellow, blue, and we mix them together, what do we get? Well, red plus blue equals purple. Red plus yellow equals orange. Yellow plus blue equals green. And red plus yellow plus blue equals black. The reason this works this way is really not all that hard to understand. When we see an object that is painted red, we are seeing light that is being reflected off of that object. All of the other colors are being absorbed. When we mix in other paints, blue, which reflects blue light, but not red very well, and yellow, which also doesn't reflect red very well, we end up with paint that doesn't reflect any color very well. Mixing paints together is a subtractive color mixing process. Color from a luminous light source is completely different. Sir Isaac Newton proved in the 17th century that light is composed of all of the different colors of the rainbow mixed together. While it's obvious that a prism creates a rainbow spectrum, before Newton it was not obvious whether the rainbow of colors was an inherent part of the light or whether it was something that the prism did to the light. By isolating a single color of light and passing it through another prism, Newton proved that green light, for example, really was green. Newton didn't exactly have ready access to convenient electric light sources of different colors, but we do today. If we mix together some primary colors of light, let's say red plus green plus blue, we get white. Mixing light together is an additive color mixing process. So here's our fundamental problem. When we're working with our images in our desktop publishing applications and image editing software, we're working in the RGB color space, which is additive. But when we send our documents to the printer or just click the print button, we're working with inks in a subtractive color space. There's no getting around the translation and conversion, so the trick is to figure out how to estimate on a computer monitor the mixing of color in a subtractive color space on a printed page. In our subtractive example here, we used primary colors we all learned in primary school, red, blue, and yellow. When printing with inks, different fundamental colors are used: cyan, magenta, and yellow. Theoretically, mixing these three colors together yields black. On a perfect digital computer, this is true. In the real world, you get sort of a dark, muddy puce color. So whether you're painting a picture or just printing one, a true black is a nice extra color to have in your palette. And so we have cyan, magenta, yellow, and black, or CMYK, which is the four color space we most commonly work with in our printed media. The K, or key separation, in the CMYK color space is important for reproducing dark areas accurately, stabilizing the color balance, and also for conserving ink. Why does any of this matter? Well, one reason is that your digital camera probably shoots RGB, and you will probably be printing your photos in a four-color process. You can convert your digital photos into the CMYK color space while you're editing, which will give you a better idea of how your image will print. Another place where this is important is when using our juice drops layered graphics. which come in PSD layered Photoshop format, RGB, and CMYK versions. If you don't need the layers, you can use the flattened RGB files for video and for the web. And for printing, you should go ahead and use the CMYK versions. In the end, there really isn't any substitute for experience with printing images, even experience with a particular printer or print shop. And none of what we talked about here matters at all if your computer monitor is not carefully calibrated. But that is a topic for another segment. For now, thanks for watching, and we'll see you next time on Techno. DVD video is the distribution format of choice for nearly all video producers. From home video enthusiasts to small event videographers to the largest Hollywood studios, DVD video discs are the most compatible, convenient, and inexpensive physical media around. There is, however, a big difference between producing 10 discs for friends and family and producing 100,000 discs for everyone and their brother. In this segment, we're going to examine DVD video distribution methods and media and how to do it right. This is Techno. The DVD video disc is a strictly defined format that describes not only the physical disc, but the data format and structure of that disk as well. As you probably already know, there's a data layer sandwiched in between two polycarbonate plastic disks. The layer reads the data from this disk, playing from the inside to the outside, following a shallow spiral groove in the polycarbonate substrate. It's not entirely unlike a reverse phonograph record. Most Hollywood movies are distributed on dual layer discs, which means that there are two data layers on the disc in addition to another plastic layer. The laser reads the lower layer again from the inside to the outside, and then reads through the semi-reflective lower data layer to the upper layer, which the laser plays from the outside back to the inside. On some older DVD players, this transition from the lower layer to the upper layer can cause your movie to pause for a moment, usually around the 45-minute to 1 hour mark. The data layer in a DVD disc is in itself quite interesting. The ones and zeros of a digitized Hollywood movie are represented by physical pits and lands, pressed into a molten polycarbonate plastic substrate that is then coated with a very thin reflective layer of aluminum metal. The plastic and metal physical format of these discs is quite robust and likely to last for a very, very long time. When we create DVD video at home, we're actually working with a disc that has a completely different physical data layer. The primary difference is that while the Hollywood discs are pressed, home-burned DVDs are, well, burned. Instead of a metallic data layer with physical pits and lands, a blank recordable DVD has an organic dye layer that is sensitive to a particular and narrow spectrum of 650 nanometer red light. A laser of the right spectrum and power can change the color of the dye to record the ones and zeros. The narrow spectrum bandwidth of the dye sensitivity means that home-burned DVDs can be exposed to household illumination or even left out in the sun without becoming corrupt. Although I would highly recommend that you not test this theory by leaving your DVDs face up on the beach or in the back window of your car. With reasonable, proper care and storage, home-burned DVDs will very likely last a long time, but probably not as long as pressed into plastic Hollywood movies. For small video production shops that typically need to create 10 to 100 DVD video discs per project, duplicating your DVDs using a DVD burner makes great economical sense. Once you hit 50 to 100 discs per project, it's very likely that you'll want to get some kind of multi-burner robot setup, but that is simply a matter of convenience. If you're planning to distribute 250, 500, 1,000 or more DVDs, you're going to want to replicate your discs by having them pressed. Because of the economy of scale, replicated discs are not necessarily more expensive than duplicated discs on a per unit basis. A ballpark figure for a run of 1,000 copies might be $1,000 or $1 per disc, which can include setup, glass mastering, and disc face printing fees. The DVD mastering process requires professional DVD authoring software from companies like Apple, Adobe, Sonic, or Sony, among others. When selecting your software, make sure it can author a DVD master image to the DVP 2.0 format or the newer CMF specification. Traditionally, DVD masters have been transferred, ironically, to DLT or digital linear tape, which means you'd need to buy a DLT tape drive, a SCSI interface card, and some tapes. While this method is probably still valid, DLT is rapidly becoming old technology. Replication houses are now also accepting hard drives in an external enclosure, and in some cases, DVD data discs. The long and short of this very technical discussion is that you need to get this exactly right. I'd strongly recommend shopping around and finding a replication house first and ask them what they need from you and what they recommend. If you can't find anyone at the replication house that can help you at this phase in your project, then you should probably thank them for their time and find someone who does have the time to walk you through this process. Authoring DVD masters for press replication is clearly a professional task that requires more than a quick 7-minute overview, but I hope we've at least pointed you in the right direction for further research, because that's all the time we have for today. Thanks for watching, and we'll see you next time on Techno. Color is important. Color is so important, in fact, that we've devoted a good percentage of the time in these segments to discussing it. We've discussed white balance and color temperature, additive and subtractive color spaces, RGB, YUV, CMYK. Color, in theory, is a very deep and interesting topic. In this segment, however, we're going to bring all of that theory together to one pragmatic point and show you how to get color right by calibrating your gear correctly for video and print. This is Techno. Let's start here with calibrating an NTSC video production monitor for television and DVD production in the United States. A production monitor is a special and expensive beast that uses the same fundamental technology that a CRT television uses at home. While a true production monitor is a nice thing to have both while shooting and back in the edit bay, using a less expensive consumer television, or more commonly nowadays an LCD monitor, is better than nothing at all. And in any situation, you're going to want to perform a simple calibration on whatever you use anyhow. We're looking here at our Sony production monitor. To start with, we've thrown up some bars on the monitor from our source, which would be a camera in the field or the preview output from your software in your edit bay during post. We've all seen these bars before. The technical name is SMPTE Engineering Guideline 1-1990, but SMPTE color bars is close enough for our purposes. The first quick test that I want to show you here is how to get the brightness right. There are 3 black to gray bars down here in the lower right hand section. They're known as the plugge, which is short for picture lineup and generation equipment. If you can see all 3 of these bars, then the brightness is too bright. If they all merge into one, it's too dark. what you want to do is set the brightness so that only the right-hand bar is distinct and visible. The other quick test that I want to show you here uses these strips of blue, magenta, cyan, and white. If we use a blue filter on the monitor, these bars will appear to blend together if the phase and chroma controls on the monitor are properly calibrated. Some monitors actually have a blue button which will turn the monitor gray in the case of this one, or you can use a special blue colored gel or blue colored glasses such as these. But not just any blue color will do. You need a special blue color to do the calibration correctly. When you're done tweaking the phase and chroma controls, your output will look something like this. While this kind of calibrating doesn't rise to the level of broadcast engineering standards, and it's not the same as using a vector scope on the SMPTE bars, this easy eyeball calibration works on any monitor, expensive or cheap, whether in the field or in your edit bay, and it's well worth performing. A more precise method of monitoring your source is with vector scope and waveform monitors. The ones we're looking at here are computer-based digital monitors that are part of Serious Magic's Djtv rack software, which you can run on a laptop in the field to objectively assess the accuracy of your output. Whether you're eyeballing your image quality on a calibrated production monitor or using vector scope and waveform monitors, paying attention to color before you start shooting makes a difference. Computer monitors also need to be calibrated in order to truly display colors accurately. While calibrating your computer monitor's brightness, contrast, and gamma settings is relatively easy, calibrating the color for print is anything but. When we configured our video monitor, we were looking at our real output in real time. But when we configure our computer monitor for printing, we're not looking at the real output, which is going to be ink and paper. So no matter what we do, we're only simulating the proper output on our monitor. This is very hard to do. A good beginning, however, is to calibrate your monitor using a little device such as this. This is a Color Vision Spider, which starts at about $80. Basically, you just place this little optical sensor on your monitor, and then the software runs through a series of tests and diagnostics that automatically adjust your monitor as you go. Keep in mind that what this does is make sure that your monitor is displaying a particular digital color as accurately as possible, both for print and video. The conversion from accurate colors on your monitor to accurate colors on the printed page is the other half of this process, and this is not entirely straightforward. What you see on your monitor in the RGB color space is not the same as what you get out of your printer in a 4-color CMYK printing process, even when working with CMYK images like our Juice Drops graphics. Photoshop can manage your color based on monitor and printer profiles. This changes how the colors are displayed as determined by our calibration software here. Again, what we're trying to do is estimate what the colors will look like on ink and paper. So this is an inherently inexact simulation. Here's how to perform a soft proof of an image you're editing in Photoshop. From the View menu, select Proof Setup, Custom, and select the profile of your printer, which you may need to download and install from the manufacturer. Even using one of the default CMYK settings will give you some idea of what you're up against here. Ultimately, even if your monitor is calibrated precisely and you have an exact ICC color profile for your printer, the final output on the printed page will not be precisely and exactly the same. Working with the CMYK color space and soft proofing are important steps to take, but there's still no substitute for printed proofs. And that's why, even in this 21st century, we still get hard proofs back from the printer before we run off 250,000 copies of Digital Juice magazine. Unfortunately, there's no substitute for a little experience in this area, and even some experience with a particular printer and print shop. Sometimes the exact color just doesn't matter all that much. In other situations, such as with corporate logos, identity, branding, or school colors, for example. Even amateurs will notice when you don't get the colors mostly right. Being aware of color issues and at least paying a little bit of attention to color calibration will always pay off in higher quality productions in the end. Thanks for watching, and we'll see you next time on Techno. Being visual creatures, spotting bad video is easy. Audio problems, on the other hand, can be much trickier to identify. In the controlled chaos of a studio shoot, audio issues can be easy to miss. In the complete chaos of a location shoot, audio problems might be the last thing you're worried about. Back in the edit bay, however, bad audio will be impossible to ignore. In this simple, direct, and pragmatic segment, we're going to tell you what you need to know about an electronically clean audio signal path from your microphone to your gear. Because the old joke really is a joke. You can't fix it in post. This is Techno. We've got great mics and solid recording gear, but the audio from the best mic in the world is worthless without the right connections. We wouldn't be having this discussion if there was one single standard for analog audio connections, but unfortunately that's just not the case. Let's start with the 3-pin XLR connection, which is found on basically all professional microphones. This is known as a balanced connection, and the 3 pins and the wires in the cable work like this. Number 1 is a grounding wire, which can also act as a shield. Number 2 is a signal wire. And this third wire carries an out-of-phase signal that balances the signal wire. The third balanced wire's polarity is inverted, or 180 degrees out of phase, with the primary signal wire. The idea here is that any extra noise that's introduced into the cable along the run is canceled and eliminated at the receiving end by the out-of-phase signal. In a completely balanced system, this is indeed what happens. Unbalanced audio cables can only realistically be run for a couple of meters without problems, but balanced cables can and often do run for 10, 20, or 30 meters or more. Unfortunately, we don't always have the luxury of working in a completely balanced audio system. Ever since the advent of the Sony Walkman, the most common connection on consumer camcorders and computers is the 1/8" mini plug. Professional microphones, however, almost always have a balanced 3-pin XLR connection. It's easy enough to pop into your local radio hut and find an XLR to mini plug adapter for a couple of bucks. And you know what? Sometimes it'll work. More often than not, however, it won't. And this is what you'll hear. Let's be clear here. This isn't a matter of the quality of the connector, and buying expensive gold-plated adapters and cables will not fix this problem. This sound is a 60 Hz hum, which, not coincidentally, matches the frequency of our alternating current electricity in the United States. There are also harmonics in there that you can hear at 120 Hz, 180 Hz, and 240 Hz, and so on. The difference between a hum and a buzz is that a buzz has more of these overtones present. The 60 Hz hum is caused by a voltage differential between various pieces of audio gear in your system, and it can potentially creep into the audio signal path either by radiation of the power signal through the air or directly through connected electrical wires. Shielded, balanced cables can help eliminate this interference, but they aren't a cure-all.
The easiest, safest, and least expensive way to kill a 60 Hz ground loop hum is to unplug your gear from the wall. If your chute is short enough and you have enough batteries and backups, running XLR cables to your camcorder and simply converting to the mini plug with your adapter will be about all you need to do. When you connect a professional microphone to a consumer camcorder, even a good one, you're going to need to convert from a balanced signal to an unbalanced one at some point in the signal path. There are quite a few simple passive adapters you can get. The most common ones simply connect the ground and the signal pins to the left channel and ignore the third balanced pin entirely. Since basically all professional microphones are monophonic anyhow, this is all you will need to do, except that back in your edit bay you're going to need to duplicate the left channel to the right channel. One warning here, be very cautious about using an XLR to stereo mini plug adapter to send a balanced signal to both channels. The left and right channels can and will cancel each other out. One item that may help with our 60 Hz hum problem in very particular situations is a ground lift. The 60 Hz hum is introduced into the system because of voltage differences between your gear, and eliminating the ground in a particular part of this audio path will fix the problem. One way to effectively eliminate a ground is to simply not connect the ground pin at all with one of these little buggers that you can buy at the hardware store for about 25 cents. Notice that I said effectively eliminate the ground and not safely eliminate the ground. This will indeed stop the 60 Hz hum in many situations, but it is not recommended, especially with expensive audio video equipment. If you're connected to the wall, something in the path needs to be connected to the ground for safety's sake. There are special ground lifters designed for audio equipment, but generally speaking, these will not work for simple microphone to camcorder audio systems. Since the hum is caused by voltage differentials between various pieces of equipment, and in this situation, there really aren't all that many pieces of equipment involved. Another simple device that can work on an audio connection is an isolation transformer. This device allows the signal to be taken from one device and fed into another without electronically connecting the two circuits. For microphone to camcorder connections or microphone to computer connections, it would be great to have a device that can also deal with different impedance levels as well. For the sake of keeping this discussion short, let's just say that your CD player or iPod outputs a high Z line level signal and your microphone outputs a low Z mic level signal. Consumer camcorders and computers are generally very tolerant of consumers plugging the wrong device into the wrong hole. For example, plugging an iPod into a mic jack. Theoretically, plugging a line level signal into a mic level input could seriously damage your equipment. In practice, however, it rarely does. The consequence of this is that when you plug a professional mic into a 1/8 inch mic input, the levels from the mic just aren't going to be high enough. So what we really need are two pieces of equipment to get our low-level microphone signal into our consumer gear. First, we need some sort of XLR to mini plug adapter, and second, we need something that can boost the signal a bit, like a mixer or a small preamp. Fortunately, this is not an uncommon problem, and there are a number of solutions. This little device I'm looking at here is generically known as a direct box. Direct boxes come in many different configurations and convert inputs to outputs of all sorts. As you can see on this one, it's got a ground lift and a mic line level switch and a gain potentiometer here on the front. You can get a decent direct box for somewhere around $100. Beachtech offers a range of really solid products with level controls that will handle getting professional mic signals into your camcorder and computer very, very well. And on the computer-only end, you might want to look at M Audio's Fast Track USB, which will actually perform an analog to digital conversion of the microphone signal before sending it to your computer. When you know you've got the right video gear and the right microphones, no production pitfalls are more frustrating than audio issues. Even though it's not quite as easy as spending a couple of bucks on a simple adapter, running balanced cables and getting a decent preamp or direct box for your microphone is definitely worth the money. Thanks for listening, and we'll see you next time on Techno. We get quite a few questions for and about Djtv every week. One of the most common ones runs something like this. Dear Djtv, what compression are you using on your website to make Djtv look so good? This is a very good question, but it's actually two questions in one. First, why does Djtv look so good? And second, what compression are you using on your website? We're going to answer both of these questions in the next few minutes as we explore video compression on Techno. Just why does Djtv look so good? The answer to this question actually has very little to do with compression. Djtv looks better than most of the video you see on the internet, often much, much better, primarily because of the production end of the process. In short, extremely careful attention to lighting, good equipment, and the combined experience of a dedicated team of professionals is what makes Djtv look the way it does. Don't get me wrong, compression is important, extremely important. But the compression process is much more about not screwing up your video. It's simply not possible to improve the quality of a program during the final compression phase. Digital compression is fundamentally about saving space, and smaller files are easier to transmit from one location to another, perhaps via email or on the web. Fundamentally, we're talking about minimizing the data rate, which is the total file size divided by the duration of the video in seconds. A 5-minute digitally compressed video file that is, say, 30 megabytes in size has a data rate of 0.1 megabytes per second. Data rates for the internet in general, and video in particular, are expressed in terms of bits per second and not bytes. And since there are 8 bits in a byte, we would say that our 5-minute 30 megabyte video has a data rate of 800 kilobits per second. The easiest way you can lower the data rate of your video are very non-technical. You can reduce the frame size and the frame rate. By reducing the frame size of your video from, say, 640 by 480 to 320 by 240, you can make your file 75% smaller. Reducing the frame rate from 30 frames per second to 15 frames per second can cut that data rate in half. This is obviously a very significant reduction in the total file size before we even get into any of the complexities of digital compression and encoding. Digital compression comes in two basic flavors, lossless and loss-E. Lossless compression faithfully maintains the digital integrity of the data. While losslessly compressed files can be significantly smaller than the original files, every single pixel in a losslessly compressed frame of video can be reproduced completely accurately when the frame is uncompressed. The mathematical algorithms are, of course, quite complex, but the process is something like this. Let's say we have a square frame of video that is composed of 10,000 white pixels that we want to compress. Uncompressed, we would represent it this way. With lossless compression, we might represent it like this. Or even more simply, like this. Either way, our compressor summarizes the data in the frame and makes the total file smaller.
The decompressor interprets the data and accurately recreates a frame that is identical to the original. The compressor-decompressor software is called a codec. Of course, most frames of video are not entirely composed of white pixels. If every pixel in a frame is different, lossless compression becomes almost impossible. The video you're watching now, for example, is actually fairly easy to compress. The solid, unchanging nature of the background and the high quality of the video as it is shot means that our codec can very efficiently compress this frame. If we had a very busy background, or if the lighting was poor and we had to turn the gain up on the camera, then the codec would have to spend more bits on these noisy details instead of dedicating more of the frame's data budget to the subject. This is the fundamental problem with the quality of most of the video clips you see on the internet. Shaky, handheld, poorly lit source footage is very, very difficult to compress. Lossless codecs have perfect fidelity and are therefore the highest quality you can get. Distribution codecs are, however, always lossy codecs. From the MPEG-2 encoding on DVD video discs to all of the various clips you see on the internet, everything is encoded using some kind of codec that discards and summarizes data such that you can no longer recreate the original frame with 100% accuracy. This is a very, very complex topic, both in terms of the mathematical algorithms involved and in terms of the human visual perceptual system. While the actual process of intra-frame and inter-frame compression is complex, the trade-offs are easy to understand. All other things being equal, we need to balance file size against quality. Within a particular codec, larger files will be higher quality. To get smaller files, you're going to have to sacrifice some of that quality. The exact balance and acceptable loss of quality for you is going to require experimentation. Our compression specialists here at Djtv spent a good chunk of time over the course of a week rendering dozens and dozens of experiments to find the ideal balance for us. There are many compression solutions that were considered and tested, including Flash Video, QuickTime Reel, and Windows Media. Keep in mind that this is a summary of some long internal discussions and at least a week's worth of experiments that were performed by our IT and web professionals. In the end, we decided to go with QuickTime, primarily because it fulfilled our need to be very nearly universally playable by our audience and also met our quality versus file size demands. The video on our site is not being streamed. We simply found that streaming is unnecessary for what we want to do. Instead, we've provided clips for progressive download in a few different sizes, and we're letting our audience choose what they want to watch. Progressive downloads let videos start playing before the entire file has finished downloading, but since the video is downloaded and not streamed, playback is very reliable. The high data rate clips on the site have a large frame size, and the video is encoded using Apple's compressor software to the QuickTime file format using H.264 encoding. The data rate for this video is about 800 to 900 kilobits per second. The medium data rate clips use an intermediate frame size and were compressed using the Sorensen 3 Video Pro codec in Sorensen Squeeze. We used Sorensen primarily because it gave us more options than the QuickTime Pro package does, most importantly, 2-pass variable bitrate encoding. QuickTime Pro is about $30, while the Sorensen software is 10 times as expensive, however. The video data rate for the medium clips is about 360 kilobits per second. The low data rate clips were also compressed using Sorensen Squeeze. The video data rate for these clips is around 160 kilobits per second. Compression is a very, very deep topic, and there's no absolute best format or magical one-size-fits-all settings that we can recommend for your internet video. What I hope you do take away from all of this is that the quality of internet video is primarily about quality productions from start to finish. For your video, you need to select a format that allows the most universal access for your audience and that balances quality against file size and data rate. Finally, there's no substitute for performing at least a handful of render tests. I realize this is just about the least fun aspect of creating video for the internet, but it's a necessary part of the process. Once you've discovered the settings that work for you, make sure you save the render template presets for the future. I hope we've at least set you on the right path to good quality video compression, and we'll see you next time on Techno. Although some of you have never actually seen a real glass and metal vector scope or a waveform monitor mounted in a rack of broadcast gear, this equipment is now available in all professional editing applications. And there's even a company called Serious Magic that makes virtual ones that you can use in the field on a laptop. There are two reasons why you should care about these monitors. First, they can help you improve the quality of your video, and second, they're surprisingly easy to use and understand. We're going to prove that second point to you here in the next few minutes and get you started on a new career in broadcast engineering here on Techno. Digital media and computer editing have greatly simplified the task of producing programs for broadcast over the past decade or so. Unfortunately, computer editing can also introduce technical problems that can lead to poor quality images on the television screen. An example of this is when we drop a very bright title on top of our video. The title composition can look fine on a computer, but if it pushes the video signal out of spec for broadcast, you can get significant clipping, tearing, ghost images, or even a buzzing in the audio signal. These sorts of out-of-spec signals are easy to identify with a waveform monitor. Another area where objective monitors can help us is when you need to perform a color match. For example, when you need to get the color of a product or brand exactly right, you can verify your shot on a vector scope, or you can use your editing software's monitors to line up and match multiple cameras more accurately. In any case, vector scope and waveform monitors are much easier to read and use than you might think. So let's power up our gear and send a signal through it. A vector scope is a special type of oscilloscope that displays an XY plot of the two chrominance channels, the U and the V in the YUV color space. This circular reference overlay is called the graticule, and the green line that the oscilloscope draws on the screen is called the trace. The amplitude of the trace from the center of the vector scope measures the saturation of the chrominance signal, while the position of the trace around the circle measures the hue. Let's take a look at these targets on the graticule. We have red, green, and blue targets, as well as cyan, magenta, and yellow. If we throw a solid, fully saturated red on the screen, the trace should land right at the center of this red target. Here's the distinct pattern you'll see if you send a set of NTSC color bars to a vector scope. The fully saturated colors go all the way to the center of the targets. Decrease the saturation and the trace shrinks. If we adjust the hue on the bars, you can easily see the pattern rotate out of phase. You've probably seen the NTSC color bars and heard the 1 kHz tone at the beginning of a tape meant for broadcast. When viewed on a vector scope, a broadcast engineer uses these bars to verify the technical quality of a program and calibrate the chrominance and luminance levels for it. A vector scope can also be used in the field or back in the edit bay to line up or match different cameras used in a multi-camera shoot. By pointing all three cameras at something white, you can white balance them manually. You can immediately and precisely see the difference between the cameras on a vector scope.
The trace here should be exactly in the center of the plot. By adjusting the camera's RGB color levels, or even easier, adjusting the color back in your editing software, matching shots is fairly easy with a vector scope. Vector scopes are almost always paired with a waveform monitor, and the two devices together can really tell us a lot about our signal. Like the vector scope, a waveform monitor is also a special oscilloscope that displays the voltage levels of the various lines in a video signal over time. This corresponds directly to the luminance or brightness. Essentially, a waveform monitor can be thought of as a light meter of sorts. There are some other broadcast engineering type signals that can be seen on a waveform monitor, such as the color burst, the vertical blanking interval, closed captioning, and even the V-chip rating system. For our purposes, however, we're going to limit our discussion to the video levels. The horizontal lines on our waveform scale here go from -40 to over 100 IRE. The unit here is the IRE, which is named after the Institute of Radio Engineers, which first developed the scale. 0 IRE is considered blank, and 100 IRE is white, with -40 IRE reserved for a sync signal, and the over 100 IRE levels are for transient peaks. The levels in an NTSC broadcast legal television signal in the United States span from 7.5 IRE, which is black, to 100 IRE. A signal that averages over 100 is going to be blown out and overexposed. If your camera has a zebra stripes feature and you set it to 100%, all of the zebra pattern areas would show up on a waveform monitors at levels that average at or above 100 IRE. Now, this doesn't mean that the video is wrong, it just means that you aren't getting any detail in these areas, which is fine in this particular shot, for example. What you want, of course, is a subject that is properly exposed, not too dark and not blown out. And we can see this very clearly and with absolute certainty on a waveform monitor. Properly exposed subjects will come in between 70 and 100 IRE with some transient peaks over 100. And that, in a nutshell, is what these two monitors are all about. With a vector scope monitor to analyze the color and a waveform monitor to analyze the brightness, we can objectively assess the quality of our video with some confidence. I hope we've convinced you that the vector scope and waveform monitors can both be important when shooting and back in the edit bay. I hope you can also see how accessible and easy the vector scope and waveform monitors are to use. So fire up your editing application and check out the monitors before you render out your next project. While some people consider them to be the bane of modern existence, the computer is an integral part of an editor's life for 8 to 12 hours a day. Whether you're editing video, graphics for print, or web pages, digital media production requires a little more performance than your typical email and office machine has. In this segment, we're going to walk you through the specs of a competent editing box as of early 2007, here on Techno. Good editing computer is necessary for anyone wanting to create media for print, television, or the internet. The good news is that just about any new computer is going to be able to edit video and large images pretty well, whether you get it from a big box superstore, ordered online, or have a custom machine built for you by a company that specializes in multimedia. Our discussion today is going to be limited to new computers and not upgrading your current box. And while we're going to cover specific components you should look for, this segment will not teach you how to build your own computer. Basically, your computer has 3 primary components that are important for performance: the processor, some temporary memory or RAM, and some permanent storage on a hard disk.
For basic image editing and mini DV camcorder video destined for DVD video discs, you can get a decent system for less than $1,000. Any new computer with a FireWire port and a DVD burner will have a processor that's fast enough. But I'd plan on getting a gigabyte of RAM and a second hard disk for media storage, especially if you're editing video. But let's move beyond the basic box and into something a little more professional. Let's assume you don't have an unlimited budget to buy the latest dual CPU Mac Pro with 16 gigabytes of RAM and 30 terabytes of storage paired with 30-inch Cinema HD displays. But let's also assume that you've graduated from iMovie and are ready for some professional level editing software. We're talking about Final Cut Pro, Vegas, and After Effects level software. Realistically, we're talking about $3,000 to $4,000 for a mid-range, competent, serious starter system. As of early 2007, this is what I generally recommend. I look for the second fastest machine I can find. The latest and greatest technologies always carry a premium, and from a price versus performance standpoint, yesterday's fastest machine gives you today's best bang for the buck. Technology changes so quickly that you might think it'd be difficult to recommend a specific processor. But as of this moment, an Intel Core 2 Duo running Windows or OS X is the way to go. There isn't anything wrong with AMD, and for the past 2 years AMD has been the speed champ because of superior dual-core implementation. But for now, Intel has regained the upper hand. Briefly, a dual CPU has 2 processors on a single chip. Most simply, this would let you run your editing app on one processor and everything else your computer is doing on another. Normally this wouldn't really result in much of a performance increase since you probably aren't running a lot of other demanding applications at the same time as you're rendering. Fortunately, most editing applications are multi-threaded, which means that they take advantage of both processors at the same time, running calculations in parallel. So, for example, the software could render frame 1 on one processor and frame 2 on the other processor, or even divide up different blocks of a single frame to multiple processors. Actually, there's a significant amount of computational overhead involved in splitting and coordinating processes and in communication between the various processors. So a dual-core CPU is not twice as fast as a single-core CPU. But the performance advantage is dramatic with certain applications, such as professional-level editing software. Let's move on to memory, which is a relatively simple discussion. For editing performance, I'd consider 2 gigabytes of RAM to be a good start. 4 gigabytes won't go to waste, but the performance increase from 2 gigabytes to 4 gigabytes is not as dramatic as what you'll see going from 1 to 2. 8 gigabytes is probably overkill for most people, and 16 gigabytes is strictly reserved for the very wealthy. One area where more is better in terms of RAM is with RAM previews. Professional editing applications have a feature that allows you to send full quality finished previews to RAM. This isn't generally something you're going to do all of the time, and most of your editing previews will be real time, but occasionally you might want to render a small section of your project out at full quality, and dynamic RAM previews are really useful for this. For storage, a 160 gigabyte, 7200 RPM hard disk is a good start for your primary operating system hard drive. But you're also going to need a secondary media drive. 300 gigabytes is a good start, but hard drives are a little bit like basements or garages. No matter how much room you think you have, you're still eventually going to fill it up. Make sure your computer uses the serial ATA interface for hard disks, and of course, get the drives to match. Although the older IDE interface is fine, a computer that still uses that technology is, well, older. While you'll need special drives or fast arrays of drives for uncompressed video, standard 7200 RPM drives are all that's required for DV and high-definition HDV video. My magic buy price for hard disks is 25 cents a gigabyte, usually after a rebate. Just don't forget to mail in that rebate right away anyhow. If you need some portability between machines, an external enclosure for your media drive is a great idea and will really be necessary for laptops and iMacs that have limited internal expandability. USB 2.0 or FireWire enclosures are both fine. Which brings up the subject of laptops. Let's just state this up front. Editing on a notebook is a miserable experience compared to editing on a desktop. Notebooks have relatively small screens, crappy keyboards, awkward touchpads, and tiny slow hard drives that spin as slow as 5,400 RPMs or maybe even 4,200 RPMs. Editing laptops are generally too large for coach tray tables on an airplane and are not bright enough to work outside in a park. The battery won't last that long under typical editing conditions, so you probably are going to be tethered to a wall outlet anyhow, just like you are with your workstation. And all of this is going to cost you at least twice as much as a desktop. Laptops do have their place. For business owners, you might need to pitch projects or show clients works that are in progress at their location. And you can get serious editing work done on a laptop, no question about it. Ultimately, you may still want a laptop simply because they're really cool and sexy. From one geek to another, this is indeed an excellent reason to purchase any piece of technology. Just be honest with yourself about why you're getting a laptop. Some editors really need the flexibility and mobility of a laptop, others do not. One other item I want to highlight here is the display card, which should be a PCI Express card with at least 256 megabytes of RAM. One general characteristic I would look for is a dual head card with two outputs. Editing interfaces can get quite complex, and having an interface that spans two monitors is extremely convenient. Of course, you're going to want to pick up a pair of monitors to go with that card as well. You don't need a fancy display card, and in fact, the expensive $500 cards are either for professional 3D work or for gamers, and won't generally improve video editing performance. Don't skimp on your card and get the cheapest one, however. Some compositing applications, such as After Effects and Shake, can take advantage of special features on certain professional graphics cards, so check your software to see if this is something that makes sense for you. Also pay attention to the system requirements spelled out by the software that you intend to use. Some applications, such as Avid Express, have explicit requirements for qualified systems. Finally, and most controversially, let's talk about the Mac versus PC debate. Here's a little secret about the Mac that Steve Jobs doesn't want you to know. It's a computer. And since both Macs and Windows boxes are now stuffed with the same Intel Core 2 Duo processors, the same RAM, the same hard disk, the same display cards, and a mouse with multiple buttons, it just isn't possible to claim that Macs are inherently faster or better at editing than any equivalent Windows machine. Well, unless you're an Apple marketeer or you've been drinking too much of the Apple Kool-Aid. So here's my anti-switch campaign. If you are comfortable in a Windows environment running software from Avid, Adobe, or Sony, and you're looking for a new computer, you should stick with a Windows machine. Sure, a $3,000 Mac Pro is probably faster and more stable and better at editing than your current Windows box, but I bet a brand new Windows machine is faster, more stable, and better at editing than your current Windows box too. On the other hand, if you're just starting out and looking for your first professional level editing computer, the Mac is an excellent platform that I have no hesitation recommending. In fact, this segment was edited on a Mac, but not entirely. Our senior animator, Brent Milby, works on a Windows machine, and so does Mr. Audio Buzz, Jeff Early. Which just goes to show you, it's really not about the tools or the technology once you get above a certain minimum level of performance. Shop smart. As of early 2007, get the second fastest Intel Core 2 Duo machine you can find, 2 gigabytes of RAM, and as much hard disk space as you can afford. You can expect to spend about $3,000 to $4,000 for a base system that will edit DV, HDV, and author DVD movies. Don't fret about the right time to buy either. It is an unfortunate truth that computers depreciate in value faster than new cars. So you just have to pick your machine, pick your moment, and take the plunge. Thanks for watching. We'll see you next time.
In the world of video cameras, bigger is better and more expensive is more professional, right? Well, sort of. Fortunately, the technical characteristics and features of a professional camera are actually fairly easy to define and understand. The next few minutes, we're going to go deep inside the camcorder, focusing on the CCD, showing you not only how it works, but why it's important, here on Techno. Let's start with the deceptively simple and obvious. Light from our subject enters the front of the camera through the lens. While it's tempting to call that an explanation and move on, stop and think for a second how important this is. First, our scene needs to be illuminated properly. This is both literally and figuratively outside of the camera and outside of the realm of this discussion. But I would argue this. Good lighting is the primary difference between professional video and amateur home movies. In the real world of event videography and E&G, however, running gun shooters often have to live with poor lighting. So low light performance is an important characteristic, and this starts with the lens. Quite simply, larger diameter lenses capture more light. Think about those gigantic telescope lenses and mirrors. Once we've stepped through the glass, the next hurdle for the light is the aperture. The aperture is primarily used to get the exposure right. Not too much light, not too little. It also controls the depth of field, which is an extremely important artistic tool. In short, opening the aperture gives you the most control of the depth of field and focus. While we aren't going to spend any more time on this important tool in this segment, suffice it to say that the correspondingly smaller lenses found on compact, convenient consumer camcorders have limited control of the depth of field. Along with the aperture, the other factor that controls the exposure is the shutter. Fast shutter speeds mean that the shutter is open for shorter periods of time, which decreases the amount of light that gets through to the CCD. The shutter also controls the amount of blur you get on a single frame of video, which in turn affects the feel of full motion video. This brings us to the image sensor, which is a CCD in most of today's camcorders. In reality, we had already arrived at the CCD just a moment ago when we discussed the shutter. Most consumer camcorders do not have a physical shutter, but instead determine the duration of the exposure electronically. In any case, and to summarize a great deal of sophisticated electronics in a sentence or two, once the light hits the CCD, it is converted into an analog electrical signal and sent to another chip where it is digitally processed. This processing includes error correction, filtering, white balance, and color transformation, among other things. Oftentimes, this all happens on a single dedicated media processor chip. Newer and cheaper CMOS technology incorporates the light gathering and processing circuits all on the same chip. Generally speaking, while CMOS chips are more efficient and cheaper to manufacture, CCDs are less electronically noisy and produce better quality images. Image sensors are obviously a lot more complex in the details, vary in their sensitivity to light and the quality of the images that they produce. Increasing the sensitivity can increase the amount of electronic noise, however. Professional camcorders have gain controls to vary the sensitivity of the chip and thus the level of the noise. In most situations, you'd want to leave the gain at 0 dB and control the exposure with the aperture and shutter. Some cameras have a simple low, medium, high toggle, and some give you a little more control over a range of values, for example, plus or minus 12. Increasing the gain to plus 18 dB is very likely to introduce noise into the picture. Pragmatically, however, if plus 18 means getting the shot, as opposed to not getting the shot, a little noise is just the price you pay. Larger CCDs with more pixels are clearly better than smaller CCDs with less pixels. Larger CCDs have better low light performance, while more pixels means better resolution.
For example, under the same conditions, a small consumer camcorder with a 1/6 inch CCD will just not be able to produce as bright an image as this Panasonic Djtv X200 can with 1/3 inch CCDs, or as bright as this $60,000 Vericam can with 2/3 inch CCDs. There isn't a straight relationship between chip size and the number of pixels, however. The CCD also determines the aspect ratio. HD cameras, for example, have a proper 16:9 aspect ratio by default. You might be surprised to learn that CCDs don't record in color. Individual elements in an array only detect and record the intensity of the light hitting them. And color is actually added to the image data later during the processing phase. If a single CCD is used, individual elements in the array are actually dedicated to record only one color in the RGB color space. This is done by placing tiny color filters in front of individual elements. The first pixel in an array, for example, might have a red filter in front of it, and therefore only record the intensity of red light. The pixel next to that one might have a green filter and record green light. And so the array of pixels that make up the CCD is covered by a very fine color filter array. The exact nature of this filter depends on the design of the chip, but the point is that the CCD is not capturing a full resolution version of the color information. The CCD does record a full resolution grayscale image. And since the human eye and visual perceptual system are more sensitive to differences in brightness than to color, this is an elegant and economical solution. Furthermore, the image data will eventually be encoded with some type of digital compression. For example, DV25 in the case of mini DV camcorders. And this almost always involves some sort of color sampling anyhow. Professional camcorders capture color at full resolution using 3 individual CCDs, one for each color. Between the lens and the CCDs is a beam splitting prism, which splits the light up into its component RGB colors, which are diffracted off to individual CCDs that then record the intensity of the light in each color at full resolution. The lens itself in such a system is more complex, and the addition of the prism block, 2 more CCDs, and the circuitry to integrate them makes 3 CCD camcorders comparatively more expensive than single CCD systems. But this is something to look for in a professional camera. Once the light is captured, the image is digitally processed and stored to some medium. The media itself in this digital age is relatively unimportant. In the recent past, it's been videotape, but optical discs, hard disks, and solid-state media are all becoming more common. In all cases, the recording media is finite, which means that some kind of digital compression is used, and this is relatively important. The most common compression for consumer camcorders to mini DV tape is DV25, for example. Camera phones and consumer optical disc cameras often use much more efficient compression, but that also compromises the quality even more than DV25. On the professional end, there are a host of less compressed formats, all the way up to and including uncompressed signals sent directly to hard disk from the camera. Here's the application of all this theory. When shopping for a professional camcorder, look for large glass, 3 large CCDs, and less compression. You might also look for interchangeable lenses, XLR microphone inputs, and lots of manual controls. While the consumer realm is filled with a bewildering array of models and features, in the professional realm, you're only going to find a very small number of camcorders, perhaps only 3 or 4 at any particular price point. This will make your comparison research much easier. Finally, if you can't afford a Vericam, shoot the best video you can with the best camera you can afford. Modern camcorders, even inexpensive consumer ones, shoot truly brilliant video, and a Vericam isn't the remedy for lame content and poor technique anyhow. Thanks for watching, we'll see you next time. When you buy a digital still or video camera, you're primarily paying for two things: a fancy megapixel imaging chip and some precisely engineered glass in the form of a lens. The image sensor, while interesting, is probably so complex that it defies a simple explanation. The lens, however, still follows the same rules of optical physics that governed Galileo's universe. In this segment, we're going to dissect a camcorder lens on a virtual optical bench, show you what all those lens numbers mean, and explain why they're important as we step through the looking glass on Techno. The tiny lens on this camera phone here probably cost next to nothing to manufacture. The Fujian on our Vericam, however, retails for tens of thousands of dollars. And extreme zoom lenses can cost nearly $200,000. When you're shopping for a digital camera, you can pretty much estimate the price if you know two things. First, how many megapixels are on the image sensor, and second, what's the power of the optical zoom. It's really all about the glass. Let's start our discussion with a look at a simplified lens. Here we have an objective lens at the front and a focusing lens that can move back and forth to create a sharp image on the focal plane. This is fundamentally how all lens systems work. In a camcorder or digital still camera, we'll put a CCD at the position of the focal plane, of course. Crisp, clear focus is the obvious goal here. But as those of us who are getting older can attest, focus is more than just a matter of in focus or out of focus. So, for example, when something near the camera is in focus, the distant background might be out of focus, or vice versa. The focal length of a simple lens is the distance from the center of the lens to the focal plane. In a complex lens system, the discussion is, well, more complex, since the center of the lens often means the center of the lens elements that make up the entire lens. The focal length of a lens is listed in the specifications for a camcorder or lens and is measured in millimeters. For example, let's say we have a smallish camcorder lens here that has a focal length listed as 5 to 50 millimeters. If we divide 50 millimeters by 5, we get 10, which is, not coincidentally, the optical zoom power of this lens, 10x. Longer focal length lenses are called telephoto lenses. The minimum focal length is the shortest you can go and gives you the widest field of view. The actual zoom elements of an afocal lens system are at the front of a lens, and in the simplest configuration require 3 chunks of glass. As the middle piece of glass moves back, the zoom increases. Zooming in on something also reduces the field of view. Short focal length lenses are referred to as wide or wide-angle lenses. Wide fields are especially nice when you're shooting in a small interior space where getting everyone to scrunch up together for a group shot can be tough. The other stat besides focal length that you will commonly see listed for a lens is the f-stop or f number. Most simply, the f-stop is a ratio of the focal length divided by the diameter of the lens aperture. So in the simplest situation, an f-stop of f1 on a lens with a 50 millimeter focal length means that the lens aperture itself is 50 millimeters wide. Changing the f-stop changes the aperture, which controls the amount of light entering the camera. Smaller f-stops mean wider aperture, which seems odd at first. f1 on a 50 millimeter focal length lens means a 50 millimeter aperture. f2 means a 25 millimeter aperture. Remember, this is a ratio of the focal length to the diameter. So larger f-stops mean larger divisors and smaller apertures. The speed of a lens is determined by its maximum aperture setting. f1.4 is considered to be fast. More light coming in means you can use faster shutter speeds. It's easy enough to understand that smaller apertures mean less light for the exposure, and at a most basic level, this is what the aperture is for.
But a wider aperture also means a shallower depth of field, and thus more selective control over what is in focus and what's not. Longer focal lengths also mean a shallower depth of field. Taken together, you get the shallowest depth of field and the most artistic control over your focus with your camera when the aperture is wide open and you're zoomed in as far as possible. The only catch here is that you need a wide aperture, which means a larger lens. Small, convenient consumer cameras with smaller lenses have smaller apertures, and thus relatively less control over the depth of field. Real-world camcorder lenses are more complicated than what we've presented here, with more precision elements and features like teleextenders that double the zoom and optical image stabilization. The lens complex can easily account for at least half the cost of a consumer camcorder, and in the professional realm, the lens can easily cost more than the camera body itself. So let's review what we can tell about a lens based on manufacturer reported numbers. First, we have the focal length range. A 2.5mm focal length is considered short and provides a wide field of view. Second, we have the f-stop, which is expressed as a ratio of the focal length and defines the size of the aperture. It is a ratio, so smaller f numbers mean larger apertures. Finally, we have the filter diameter, which is especially important if your camcorder has a fixed lens, since the threads on the barrel will let you add 2x teleextenders or wide-angle adapters. While our trip through the looking glass certainly wasn't as interesting as Alice's, I hope you found this to be time well spent, because the lens is easily one of the most important and expensive parts of any camera. With that in mind, I'd like to leave you with a recommendation. Find the filter diameter of your lens and get a clear or UV protector. Get an expensive one or get a cheap one, but get one, because damage to your camcorder's lens is a $500 accident waiting to happen. At least. Until next time, happy shooting. When DV first hit the scene a decade ago, the only way to distribute your movies was on ancient and inferior VHS tape. Even so, the quality and editing convenience of mini DV made it the clear choice for professionals of all sorts. It wasn't until the DVD video revolution of a half dozen years later that end-to-end digital productions finally became a reality. Now it's 2007. And we're in exactly the same position today with HD. We could shoot it, we can edit it, but distribution is still a problem. Does that mean you should wait to make the leap to HD? We'll answer this question and more as we discuss HD distribution on Techno. Getting your production company into HD is somewhat expensive, but very doable. All told, including a camera, an editing system, and an HD monitor or television, you're probably talking about a minimum of $10,000 just to get started. And although you'll be able to hook your camera up directly to your television to see your HD footage and programs in all of their high-res glory, 10 grand isn't enough for anyone else to see your productions. In many ways, the situation we're in today is exactly the same one we were in with DV a decade ago, pre-DVD video authoring and distribution. In other ways, our situation is very different, and we are actually in a much better position today, because HD distribution is already a reality, and it has been for years. In the realm of corporate broadcasting and network television, HD distribution has been at least a possibility since digital transmissions began. Digital cable and satellite have been around for years, and now digital over-air broadcasts are becoming more widespread, especially since the government has mandated the transition to digital by 2009. Digital is not necessarily the same as HD, however.
but digital does make HD a possible format for distribution. Let's first define what we're talking about. Standard definition is any format with less than 700 lines of horizontal resolution, which means anything from analog broadcast television, VHS tape, all the way up through DVD video. High definition video has 700 or more lines of horizontal resolution. This includes the two primary broadcast resolutions of 1280 by 720, aka 720p, and 1920 by 1080, aka 1080i. Standard definition DVD video is the most successful consumer electronics technology ever, so it's not unreasonable to assume that some sort of optical disc format might be in the future of HD. Indeed, two major technologies are currently competing in yet another format war: Blu-ray and HD DVD. Both optical disc formats use shorter 405 nanometer wavelength blue-violet laser light instead of the red lasers found in today's DVD players. The shorter wavelength light allows greater data densities, which means that you can store more on a disc of the same physical size. It should be noted that both types of discs hold exactly the same digital data, so the media format does not affect the quality of the video at all. There are, however, some technical differences between the two competitors. In summary, Blu-ray's tighter track pitch means greater data densities, which means you can squeeze more data on the disc. But if the failed beta tape format is any indicator, however, technical superiority isn't a good predictor of a format's ultimate success. And as of early 2007, HD DVD players and pre-recorded media are substantially cheaper than Blu-ray. Hybrid playback devices have been announced that will play both disc formats, so at least part of this discussion is moot anyhow. And ultimately, most consumers don't care about the format, as long as it works. Different industry players have already signed on and endorsed this or that technology, and while Blu-ray currently has a healthy lead in this regard, it is interesting to note that many companies are wisely supporting both formats. So the short answer for content producers is wait. Blu-ray and HD DVD burners are both expensive, the blank discs are expensive, and the first authoring tools are just starting to come out. More importantly, high-definition televisions and optical disc players are still well within the realm of the enthusiasts and early adopters, which is a fairly limited and geeky audience. Although the number of households with HD televisions and Blu-ray or HD DVD players that are not gaming systems is very, very small, many people already have HD monitors and playback devices ready to go today in the form of a personal computer. So one possible method for true HD video distribution is on standard ubiquitous DVD data discs played back on a computer. In fact, the first HD movie I ever saw was a Windows Media 9 demonstration of Terminator 3 burned on a standard data DVD disc. The only downside to this is that the vast majority of people don't have, and more importantly, don't want a computer in their living room. And although all of the big manufacturers insist that this year, 2007, is the year of convergence for the home theater and the computer, that's a claim I've heard a few times before. Wouldn't it be great if there was a standalone DVD player that could play back HD data burned to a standard DVD video disc? Chinese and Taiwanese manufacturers have developed the enhanced versatile disc and the forward versatile disc formats, which do exactly that. Since most DVD players are made in China, it's not unreasonable to assume that many, if not most, future DVD players will support both EVD and FVD. Now, one limitation to both the EVD and FVD formats is that the authoring tools are currently almost non-existent, and both formats will likely only be popular with enthusiasts and hobbyists without Hollywood and industry support. Neither of these formats will ever go mainstream.
Once again, we had a situation just like this in the late 1990s before the DVD video era, when the VCD and SVCD formats let you burn video to cheap CD discs. The formats were huge in Asia, but both completely failed to catch on in the United States. EVD and FVD are very likely to suffer a similar fate. While we've been talking about the future of HD distribution, the future has already been here for a number of years already in the form of broadband internet connections. While this method of distribution also currently involves a computer, it looks like standalone living room players of one sort or another are in the works. This development is at least part of the reason why I believe that our current DVD video disc technology is the last physical format we will ever see for movie distribution. If adoption of broadband movie downloads outpaces Blu-ray and HD DVD, it will be the death of both of those formats. The biggest problem with distributing your video in any format is still your audience. They don't want to watch movies on their computers. They don't want to spend $1,000 on a new disc player. Heck, most people don't even want to spend $200 on a new disc player. And here's the reason why. Current DVD movies look fabulous on HD television sets. And they look even better with DVD players that have dedicated scaler chips to upsample SD video to HD. Sure, it's not true HD, but for most people, it's more than good enough. So how should you distribute your HD productions? The answer is plain old standard definition DVD video discs. Unless you're producing programming for HD transmission over satellite, cable, or digital broadcast, there really aren't any viable options right now. That doesn't mean that HD production is something you want to avoid. Djtv is shot and edited entirely in HD, but it's most commonly watched at resolutions of less than 320 by 240. And once a season is finished, we release the programs on standard DVD video discs, complete with extra features. Is all that extra resolution and quality going to waste? We don't think so. From the moment you roll tape until the moment you send your project off for distribution, modern multimedia production involves a lot of storage. When a project is over, there's still the matter of archiving your media, either for posterity or just as a matter of course. In any case, figuring out what to do with your hundreds of hours of work is something that needs to be thought through carefully. And that's what we're here to do on Techno. Traditionally, video production has involved magnetic tape. Since tape is relatively inexpensive, the original field master tapes are always a part of the archive and are never reused or recorded over. Archiving your video projects on your computer can be a little bit more complicated. The video project file itself, along with all of the graphics, animations, music, and sound effects, can often be burned to a 4.5 gigabyte data DVD disc. The captured video clips, especially for longer projects, are usually too large for DVDs, however. Many editing applications have a project management feature that lets you consolidate your project's media, discarding unused material and trimming clips, perhaps preserving handles of a few seconds at the beginning and ending for future editing flexibility. Short projects, such as 15 and 30-second commercial spots, can often be completely backed up to DVD data discs. And since you can get DVD data discs for as low as 3 cents a gigabyte, this is a very cost-effective solution. Once projects exceed the size of a single disc, backing up to DVD becomes more inconvenient and time-consuming than it's worth. It's not always necessary or even possible to back up large captured video clips, however.
With proper tape logging, time code, and the batch capture utilities found in all professional editing applications, you can recreate and restore a project directly from the field masters. Besides backing up all of your project's source material, you'll also probably want to render out a final edit master, which you can also archive back to tape. For the DV25 format, $3 for a 1-hour tape means that mini DV tapes cost about 23 cents a gigabyte, which is fairly inexpensive as an archive format. Beyond the DV25 format, archiving projects from any tape source is basically the same, whether you're talking about HDV, DVC Pro, Digibeta, or whatever. But what if you aren't shooting tape? This program, for example, is shot using a Panasonic HVX200 camera, and we're recording to P2 solid-state memory cards. An 8 gigabyte P2 card runs a little under $1,200 and holds about 20 minutes of 50 megabit per second HD video for a cost per gigabyte of about $150, which is prohibitively expensive as an archive format. We initially explored the new optical disc formats as a possible archive solution. If we ignore the minimum $600 price tag of a new Blu-ray or HD DVD burner and only look at the cost of the media itself, we still find that the price per gigabyte of these media formats is at least 70 cents a gigabyte. While it's certainly true that the price of the blank media will fall rapidly over the next year or so, the capacity of these optical discs is only 15 to 25 gigabytes, which means that most HD projects will still span multiple discs. Furthermore, optical media is much slower than hard drives. For these reasons, we've simply been using the external hard disk drives where the projects live as our archives. When a drive is full, it gets labeled, logged, and stashed away in a fire safe. This method actually comes out pretty well economically too. By shopping around and taking advantage of rebates, you can easily find hard disks in the 25 to 50 cents a gigabyte range, which is competitive with the 23 cents a gigabyte cost of quality mini DV videotapes. We still haven't tackled digital compression for our archives because so far we've been assuming that the archive format is the same as your field master source video. It's not uncommon, however, to work with uncompressed video from animators or even from high-end cameras such as the Panasonic VariCam, which can output uncompressed video directly to hard disk. Even at 25 cents a gigabyte for hard disk storage, uncompressed HD video at 1.5 gigabits per second might cost $3 a minute to archive. It is possible to digitally compress and transcode the uncompressed video using a lossless video codec, which means that although the file size is reduced, every pixel of the original video frame can be reproduced with 100% accuracy. One example of a lossless codec is the PNG still image format, which can also be used for animations and video. While the efficiency of any particular lossless codec depends on the source video, you can see file savings of 15% or more with PNG encoding, which isn't insignificant. Other dedicated video codecs can hit much higher levels of lossless compression. For example, the Sheer video codecs can reduce the file size by as much as 50% with pixel-perfect lossless compression. Obviously, this translates into a 50% savings in the cost of your uncompressed archive media, so using an archive codec like this makes a lot of sense, although it does involve an extra step in your production workflow. Archiving may be the last step in your video project, but it should also be one of the first things you think about. A strategy with proper planning, media management, and an organized archive is not just a good idea. It'll save your butt someday. This is techno. This is techno. This is techno. This is techno. How's that? Do, 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 do. Basically, you just place the optical sensor on the screen and run through a series of tests like that, kind of. Basically, you just place this little sensor on your monitor, which the software has crashed now that I look at it, which is different. That was a good tape. Larger CCDs with more pixels are clearly better than smaller CCDs with less pixels. Pixels? What's a pixel? If we decrease the saturation, the trace shinks. Shinks. Do you know what shinks means? Basically, your computer has three primary components that are important for performance. Components. This will make your comparison research much easier. Comparison research. And so the array of pixels that make up the CCD is covered by a very fine color filter array. Do you like very fine stuff? Very, very fine. You can expect to spend about $3,000 to $4,000 for a base system. I had flubbed up earlier in there anyhow.
You were doing fine. What happened?
As we step through the looking glass on Techno, I always mess up the last line. CD formats, which let you burn video onto. I'm improvising and totally way off the script, but that's, yeah. I thought I could recover. Wouldn't it be great if there was a standalone DVD player that...
Can we do it one more time without an Andy Rooney?
One take, Franks. So until next time, happy shooting. What does this mean? Huh?
Cut.